Hi, it's Earthcomputer, and today I want to show you how some magic works. What you see behind me is falling blocks of any item, and I'm going to be showing you how you get that in survival. For a survival setup, I would recommend you watch Xcom's channel to keep an eye on that, because I am not going to be doing a block-by-block tutorial. If you want a block-by-block tutorial, then Xcom is where you should go. If you want some more information on the applications of this, then you can watch Myren's channel, where you will get OP sound quality, and like even better than mine I'm talking about. And punchster will do some hashmap animations. If you are like having a bit of problems understanding the hashmap, you can watch his channel. But I'm here to do a detailed explanation of the entire thing. It might be a long video, so I'm going to split it up into 9 chapters. So hopefully on screen now you will be able to see the chapters. Yeah, if you and hopefully with timestamps actually as well, because if you want to like skip a chapters, let's say you're already into coding, and you want to like skip sections that you already know, then you can skip to those timestamps. But yeah, this video as a whole is going to be aimed at like people who don't know how to code, just to have a lowest common denominator there. Yeah. Oh, and one last thing, credits are at the end. I am not the only person who works on this, so yeah, look at the credits. So in this section, I'm going to explain to you in a fair amount of detail how sand works, because it's important to understand this stuff. So right from the point where the sand first gets a block update like that, usually from underneath obviously, to the point where it turns into a falling block entity, we need to know in detail what is happening there. Okay, so first of all, the sand gets a block update. Let's look in the code where that is. It's right here, conveniently. So when the sand gets a block update, it calls the schedule update method. So if I go to there, it's here in the world, and that just goes straight to here. And then there's a check for instant tile tick. Since we are using instant tile tick in this falling block method, I'm just going to go into the instant tile tick code here. If instant tile tick is not on, then it will go underneath here instead and schedule the update for 2 game ticks later. But otherwise, it's the same. So if instant tile tick's on, it'll check if the nearby area is loaded, and then this is the important bit. It checks here if the current block in that position is equal to the sand block. So if for some reason, let me get this torch back. Sorry. If for some reason between me creating a block update there and the tile tick actually being processed, the block is changed to something else, then the tile tick won't be processed, so we can't change the block then. That's obviously more important when the update gets scheduled, but let's continue down the code here. If the block is the same, then we actually call this update tick method. So let's go back into here, see what that does. It calls check fallable. Then it checks the block below it, see if it can fall through it. And then we've got an instant fall check here. So either the instant fall flag needs to be off. Sorry, the instant fall flag needs to be off, and the we need to not be in a lazy chunk for the non-instant fall behavior to happen. And then there's instant fall behavior, which is again not important here. And here we create a falling block entity. And importantly here, the falling block entity is re-getting the block state from the world. So if we were to somehow change the block state between where it is checked here, so it's required to be sand here, and here when it's changed into the falling block, we will actually be able to get a falling block of something else. So just to demonstrate that, we can let's say that like here, for example, we could change the block. So to simulate that, we can set the block state at that position. Let's go for end portal frame. End portal frame. Okay. And let's see what happens. Let's check that it's actually built. Yeah, it's built. You can see that we got an end portal frame because we changed it in the right spot. If we were to change it, just to make it crystal clear, if we were to change it in the wrong spot, so not there, but in the actual, it like too early up here, for example, let's say here, set block state pos blocks.end portal frame. Come on. And then we try and make it fall. You can see that it actually didn't turn into a falling block because the tile tick was not processed because it was not sand at that point. So we've basically got our goal here, and the point of the entire falling block method revolves around this. So it's really important to understand it, is that at this point we need the block there to be sand, and at this point here we need it to be whatever we want. So for example, end portal frame. So we've got a very small window of time in between here and here. Come on over here to change the block. So I don't know about you, but I can't see a lot of code in between here. So that's on the theory for a while. In the next chapter, I'm going to lay out a plan of attack here of how we might actually change the block in between. But for now, let's just take a small detour into how falling sand actually works, because, well, firstly, it's interesting, and secondly, it's useful to know here. You might notice, if you have a keen eye, that we're not actually destroying the sand block here. So why are we not doing that? Well, it's actually a hack fix for sand duping. If we go into the falling block entity, on the very first tick of the falling block existing, it checks that the falling block, well, if the block at the position is still equal to whatever the falling block is of, and if it is equal, then it sets it to air. Otherwise, it kills itself. So if you have for example, a sand block here, but a falling end portal entity, then the falling end portal entity will see a sand block at its position and kill itself because it's not equal to end portal entity, end portal block, sorry. But if the end portal block sees an end portal, if the falling end portal block sees an end portal at its location, then it will destroy the block rather than the entity and allow it to continue. So I hope that all makes sense, that because that's kind of important to understand. But if you didn't get that, then don't worry, because the most important thing to understand is that we've got to change the block between here and here. So to start with threading, I wanted to first of all explain what a single-threaded program looks like so we can contrast a multi-threaded programming later. So this is a single-threaded program. What does it do? It does stuff. It does stuff, and then it does more stuff, and it does more stuff again, and does more stuff here. And the key point is that it does one instruction after the other. 1, 2, 3, 4. Time, by the way, is increasing downwards here. So it's doing this first, this second, this third, this fourth. It's not doing two things at once. It's doing one thing at a time in order, in sequence. On the other hand, in a multi-threaded application, you can have the computer doing multiple things at the same time. So it's split into different sequences of instructions. Each sequence of instruction is called a thread. So a thread is on its own like a single-threaded program. So a thread can do stuff, and then it does more stuff, and then it does more stuff in a sequence in increasing time, never doing two things at once. But then once you add more threads, the other threads can actually do stuff at the same time as thread A doing stuff. So thread B and thread A can literally do things at the same time. So that's the difference. And that might sound this might sound like a very simple concept, but things happening at the same time does have some very interesting implications, as we're about to see. Let's take a bit of a step away from threads for a second and take a look at this analogy. So we've got a YouTube video. By the way, this is not how YouTube works, because that would be awful. You could just overwrite the likes, but let's say that YouTube worked like this. So you have a YouTube server in the middle. The YouTube server stores a number of likes on a video, such as this mess detector video down here. So this number of likes currently is 163. Now, you've got two computers watching the same video at the same time. Two people watching the same video, and they both really like the video. They like it so much that they want to hit the like button on the video, right? But unfortunately for them, they hit the like button at the same time. And this is going to cause an interesting problem. So let's just go through this slowly. Computer A tries to hit the like button. So to hit the like button, it needs to fetch the number of likes from the server. So the server sends the number of likes to computer A, right? So the number of likes is 163 at the moment. And then, just very shortly afterwards, computer B also wants to hit the like button. So computer B fetches the number of likes to the server. Now, computer A hasn't done anything yet other than fetch the likes. So the likes are still at 163. So 163 gets sent to computer B, right? And then, you know, A and B sort of smash the like button. So they add 1 to the number of likes each. So computer A has 163 likes in it. And it adds 1 to it and gets 164, hopefully, if the computer's built correctly. And computer B also has 163 and slaps the like button and then gets 164, right? But the server still has 163 because it hasn't been told otherwise. So computer A needs to tell the server that the number of likes is now 164. So it sends basically a message saying, hey server, number of likes is now 164, and the server's like, okay, number of likes is now 164. And then computer B does the same thing. Computer B says the number of likes is 164, and the server's like, okay, the number of likes is 164. So what's the problem here? The problem is that, well, obviously we can see that 2 people have tried to like the video, and yet the number of likes has only gone up by 1. So that's a problem. It's this incorrect behavior. and there's obviously a security issue here, but that's beside the point. So the problem is that there is two programs, or not programs, two like sequences of instructions on the left and on the right. They can do things at the same time, but they are allowed to read from and write to a shared some shared data here. So this 163 and 164. Well, it's readable here from both computer A and computer B, and they both write back to the same value on the central server here, the YouTube server. And so this is actually, even though the analogy here was with entirely different computers, possibly anywhere on the planet, and a YouTube server, this is exactly the same as if all of this was in one program, and computer A was just thread A, and computer B was just thread B, and this is just some shared data in the server. Okay, so threads in a multi-threaded program, even within a single program, have this exact same issue, and it's this issue that you've got to avoid. This is called a race condition, because A and B are racing to hit the like button on this awesome video. Okay, so hopefully that makes sense. So how can threading be a potential attack vector? Well, as explained in chapter 1, we need to change the block in the world somewhere between here and over here. So now we know from what we've gained knowledge about threading that this this code here could be running on one thread, and there could maybe be another thread somewhere else in somewhere else in the game code that is capable of setting the block to, for example, end portal frames in between these two bits of code. So that's our attack vector, and this is going to be hopefully how we do it. So yeah, see you in the next chapter. Let's talk for a moment about stained glass. Stained glass, whenever you place stained glass or a stained glass pane, or you break a stained glass or a stained glass pane, it has to search downwards for beacons because, relatively well-known fact, if you place a stained glass above or inside a beacon beam above a beacon, it changes the beacon beam color to look nice and pretty. Or obviously a stained glass pane does the same thing. So it's got to search downwards for beacons to update whenever you place or break one of these. Don't ask me why it has to do this on the server. The relatively knowledgeable amongst you might know that this is something that's unnecessary to do on the server, but it does it anyway. But worse than that, let's look at the code for this, because here is the code for when a stained glass block is broken or replaced. So here you can see, so this is on the main thread at the moment, and then it schedules this code down here to be run on a different thread. We're going to call it the glass thread from now on. So we've got the main thread running code here, and then once it's scheduled this code to be run, it's just going to go out of this function again and continue whatever the main thread's doing. By main thread, by the way, I mean the main game thread, like the one that does most things on the server. And then this code down here basically searches downwards, like I explained before in the world. It searches downwards for beacons. It stops once it hits the solid block, obviously, because beacons are blocked by those. And crucially, this is running off thread, possibly at the same time as something else on the main thread, and importantly, possibly during the crucial bit of code that we had here in between here, no, not there, in between up there, I think. Oh, my IDE is going nuts. Over here and somewhere in here, somewhere in the you remember. I've shown it so many times now. Yeah, so, and then there's some other code here which is going to be important later, but I'm not gonna. There's no need to understand it right now. That's our attack vector here. It's all to do with stained glass and beacons, funny enough. So let's quickly go through the obvious way to attack this. Well, obvious to us at the time. So what you want to do is you want to place the stained glass, obviously. That's step one. You can only do that on the main thread to start with, obviously. And then you need to make it so that the glass thread accesses the chunk when it's unloaded so that it can cause population. Now that's a problem because let's just say that you can only place blocks in loaded chunks. So you need the chunk to unload before it can be loaded again by the glass thread. This is a massive problem because for it to unload, you first need the unload to be scheduled because you can't directly unload chunks in 1.12 anyway. So you first get the unload to be scheduled. Now the next problem is that if any chunk access happens to the chunk whatsoever, the unload is unscheduled again. So you need to avoid that happening. You can't have any glass thread accesses happening like here or here, or like in this time. They need to be delayed still. So the unload is scheduled. Then the unloads tend to be scheduled at the end of the tick, where the autosave is. So then you need to wait for the main thread to sleep until the next tick. You can also do it during player movement, which is the beginning of the ticks, which I suppose would be a little bit easier but less automatable. But either way, this whole thing's a rubbish idea anyway, so let's just assume that we do this. And then in the next tick, at some point after mob spawning, the chunk is actually unloaded. And it's at this point where, once the chunk is finally unloaded, we can actually load the chunk again on the glass thread. So, in summary, the glass thread is spawned around about this time when you place the stained glass up here. It's when the glass thread is spawned, and it's got to wait all of this time before it does the glass thread accesses chunk. And let's remind ourselves when it does that. It is the very first thing it does. It's right at the top of this code here. World get chunk. So it's accessing the chunk in the first bit of code, so you have to delay the code from even starting this length of time. Now, 50 milliseconds might not seem like a lot to people, but that is an extremely long time for a bit of code. And even if it's a bit less than 50 milliseconds, like say 20 milliseconds, it's hard to get that right, especially since next of all, we need to, or like even 20 milliseconds to delay no code is a long time. So next of all, we need to populate chunks, and we can't just straight up populate a chunk because population causes instant fall, which ruins the whole idea of sand falling as an entity, right? So you need to do this clever trick where you cause another population from the first population and end the second population before the the instant fall flag turns off again, and then during that time you can actually get the sand to fall, and you get potentially a falling block of anything. So yeah, this entire idea, unsurprisingly, we could never get it to work. Big X, which is very off center, I'm going to scribble instead. There we go. This entire idea was bad, we never got it to work, and the project stalled for a while then. So you're going to have to wait until chapter 5 before Coolmann came in with a solution. So the goal here is to make it so that this get block state call here, when we're trying to search for beacons, looking in the world, getting block state, we want that to somehow not find the current loaded chunk, and instead try to load a new chunk. And when it's loading a new chunk, it obviously has the potential to cause world population, which modifies the world, obviously. So, how do we do that? Well, this is where Coolmann's genius idea comes in. Load chunk, not load chunk, get block state calls provide chunk, which calls through to load chunk, which calls through to get loaded chunk. So it indirectly gets to here. So the code runs to here. From get block state. And it will search for a currently loaded chunk in the loaded chunks hash map. So this hash map here is a type long to object open hash map. That's going to become important in a minute. But the main idea is we want to trick this hash map via multithreading, via a race condition, to say that there's actually no chunk there when there is. So when there is no chunk there, this chunk is null, and the game here will then check if the chunk is null. So if there's no loaded chunk, then it will try to load a chunk from a file. So we're aiming to reach this code here, and once it loads a chunk from a file, it will call through to population if necessary. Okay, so how do we trick this hash map into returning null? Well, to understand that, we are going to have to understand, at least to a very shallow depth, how this hash map works. I am going to warn you now that this is an extreme simplification of the hash map, what I'm about to show you. It's only a small part of it's the small part of the algorithm that's relevant to understand this. If you want to understand why the hash map works and like a more complete picture of the hash map, then I strongly recommend that you go and watch punchster's video, which will have nice, pretty animations, which I couldn't be bothered to do anyway. But yeah, here is my extremely simplified explanation. So, this hash map contains an array of chunks, right? So, when we try to find a chunk, which is the get method, we look for, we start at a certain point in the array, let's say here, and we start searching forwards until we find the chunk. So we might find it here, right? But let's say that at the same time, there's another method here called remove, which removes a chunk. So let's say that the main thread is unloading a chunk. That's going to call remove. It's going to remove the chunk from the loaded chunks hash map. What remove does, I mean, first of all, it obviously removes the chunk that you're trying to remove. So let's say you want to unload this chunk. which crucially here is a different chunk to the one you're trying to get. Okay, so you remove this chunk, and then the remove method might possibly move a chunk backwards in the array, like this. Okay, so the move moves an element backwards, get searches forwards. So let's say that you do unload a chunk at the same time as getting getting a chunk on the glass thread. The get will search forwards in the array, while the remove moves backwards. So the get will sort of, if get's like halfway through here and the remove has just moved backwards, the get will just miss the chunk as it's searching for it. It's like if you're in a shopping center, right? And you're looking for someone and you're in two neighboring aisles, and the remove just goes down the next aisle and it doesn't find it. That's how falling block works. I declare this is how falling block works. You're in a shopping center and it just doesn't find this chunk because it's in a neighboring aisle. But anyway, hopefully this makes some form of intuitive sense to people. Again, go and watch punchster's video, please, if you want a not overly simplified version. But anyway, with this sort of basic understanding in mind, let's get back to the code, because the code here, we now know that this can return null if our race condition works successfully. And so we've got an unloaded chunk here, or we got the game to think that the chunk is not loaded. So it will try to load the chunk again, even though it's loaded, and then it will try to populate it. So we now have access to population inside the beacon thread, which is great. Just one clarification: the main difference here between this and the method we looked at previously, which I scribbled out, is that in the scribbled out method, the chunk that you were trying to unload was the same chunk as the chunk in the glass thread, whereas here it can be in a completely different chunk, which makes it a lot easier because you don't need to avoid accessing this glass chunk in between while we're waiting for the other chunk to unload. So that is what's different about this method, other than the complexity. And yeah, hopefully that makes sense, especially with the simplification. So then, our goal is to unload a chunk while the glass thread is doing a get block state call. So how do we do that? Well, the get block state call, the unloaded chunks needs to happen at a very specific tick phase. So I've got a tick phase diagram here. This is made by Fallen Breath. It's actually for 1.13, but it's applicable enough to 1.12 that we can use it here. And the only time you can ever unload chunks, ever, is in the chunk unloading phase down here. So we're forced to be using this tick phase for that. So this here now. So we now know that this stuff here, this is in the unload chunk phase. Okay, so to get the glass thread, to get the glass thread at all, we need to be placing a glass on the main thread, or breaking one. How do we do that? We know it needs to be as late as possible before this unload chunk. Right? So let's go back and look at our tick phase diagram again. So we've got chunk unloading here. So let's go backwards, see if we can find a place to place a stained glass block. Can we do it in mob spawning, which is right before? Not really. There's not really a way to place blocks during mob spawning. We can't really do it in that. don't think that one applies to 112. This one is nothing to do with the world at all. You can't do it in there or there. I'm not even sure that's in 112 either. So it's here. It's this this orange box here is when you have got to be placing the blocks. So this is for placing or breaking stained glass blocks manually, so by hand, like a player's got to do it. And yeah, and then you obviously have to, let me go back to the diagram here and just say that this here, that's in the player phase at the start of the tick. And you have to delay the stained glass thread from the player phase all the way until the chunk unloading phase. Well, not necessarily delay it entirely, but like, you know, you want the get block state calls to be happening down here and not up here, because they all end up happening quite quickly. So, how long of a delay are we talking about then? Well, the main thing here that takes time is the mob spawning. So we need to try and shorten that as much as possible, I believe, and also try and lengthen the time as much as possible that the stained glass threads are running for. So let me show you how we are doing that. So there's two things that we have to do here. We need to obviously speed up the mob spawning as much as possible, and slow down the glass thread as much as possible. Now, speeding up the mob spawning is something that's quite well researched already, and quite well known. So I'm not going to go through really in this video how to do that. Just search through the umpteen different other videos there are for it. So here I'm going to focus on how we slow down the glass thread instead. So first of all, the first thing that slows it down is the chunk accesses. So there is a get chunk call here, as well as loads of get block state calls inside this loop here. So these actually automatically slow down the glass thread quite a lot because of the hash map that we talked about, I think last chapter. So if we take another look at this again, if you remember this, so getting the chunk does this search here. Now normally with this hash map data structure, because of how it's designed, you do not need to search very far at all. In fact, usually not even at all, before you find the right chunk. But because of how we're doing it here, or how we've set up this hash map beforehand, this search can go on for quite a long time, and that makes finding the chunk for the get block state a lot slower than it normally is. So this is actually the first thing that we have that slows down these get block state calls. And the second thing is actually if there is a beacon found. So if it finds some beacons, then it's going to try and schedule back on the main thread to update the beacon, right, or to update the beacon color. So if it does find a beacon, then it's going to go through and add this scheduled task in the world, and that eventually goes through to this function here. Now this function, if we're not on the main thread, then we are going to hit this bit of code here, and this bit of code, this is called a synchronized block. And what this does is it makes sure that even if multiple threads run this bit of code here, no two threads can ever run this block at the same time. So that means that if there is a one thread running this code here, and another thread reaches down to here, it has to wait until this thread has finished going out of this code here before it can proceed into this block of code. So only one thread can do this at a time. That ends up creating a bottleneck because threads have to wait for each other here, and that slows down all of the threads as well. So those two things combined actually does slow down the glass threads for long enough that they can end up that these get block states happen at the chunk unload phase. So slight unfortunate requirement now that we have to place down loads of beacons because just one beacon isn't going to cut it. You need loads of them. You need to put like a whole column of them here. And obviously multiple glass being placed to be able to spawn enough glass threads that get in each other's way to even have an effect. But with enough beacons and enough glass placed, you're going to hit this this race condition pretty quickly. Okay, so we've got an async chunk load, we've got an async population. Now what do we do with it? So, the async population, we can get async block updates from. By async, obviously, I mean on the glass thread. So, what do we do with the async block updates? We could go directly into the sand to make sure that the sand, drops its not what it's supposed to. But there is a better thing that you can do, is to kind of store those block updates for later. So how do we do that? Now, first of all, I should say that I have modified, I've modded the command block here so that it doesn't react to being powered. It now just reacts to block updates. So any block update will trigger this command block. Let's just turn this lever on here, and you can see that the counter has increased to 1. So every time this command block receives a block update, the counter increases. Instant tick is on. That's important too. So when instant ticks are on, then an observer actually doubles the number of block updates going through it. So if we reset the counter again, you can see here that I can turn on the lever and the number of counts has gone up by 2. So each time I now flick the lever, it goes up by 2. And I again add another observer. You can see now that it's going up by 6. I was not expecting that, I was expecting 4, but anyway, so it's going up by 6 now, and why did I just destroy them? You now have 3 observers, and it's now going up by 12. So what's supposed to happen is each time you add an observer, you double the number of block updates that happen. Let's just add a few more observers then. Okay, let's set this counter back to 0. Once we do a block update, whoa, we now get 3072 to the counter just from one block update over here. Each time we flick this lever, and if you look closely, you can actually now start to see that this is causing a little bit of a lag spike each time. So let's just add a few more to see how well our computer can cope. Let's add maybe 4 more. And reset the counter. And we have, let's do a block update. Ooh, we've got over 10,000 block updates that have been sent now to that thingy over there, the command block. And each time we flick the lever, we're going to get this lag spike where we get 10,000 block updates. Ooh, I don't know why that lag spike was so big. But yeah, you can see this lag spike, and if we go much further, obviously we're going to lag the server so much that we crash it. So why is this useful? Why is this like what you might want to call a lag machine? Why is this useful? Well, although if the observers are triggered on the main thread, they will freeze the rest of the game. If they're triggered on the glass thread, they will not freeze the rest of the game because the glass thread is running completely independently of the main thread. So, if you update a line of observers like this, even a potentially quite long one, although you can't go too long or the game will crash a different way. Or not the game will crash, but the glass thread will stop if you do that. But if you do like a reasonably long observer line like this, you can delay the glass thread without doing anything to the main thread, and you will basically have, if you make it long enough, a constant spam of block updates to at the end of the observer line, which is not freezing the rest of the server. Okay, so that obviously, since we now have a spam of block updates that are happening off thread over here, that is much better than just having a single block update coming from the glass thread, and we're going to get way more chances to get the wraith condition on the sand block. So this is a practical application of falling block. This contraption's been made by Myren. He's gone in a much more detailed video about how this contraption works and other use cases of async observer lines. Here I'm just going to very briefly explain what's going on. So we have a carpet rule which basically allows you to get an async observer line from a beacon, so we don't have to go through all the hassle of what I've already explained in this video to get one. But obviously in survival you would have to replace this with all of that. But let's just flick the lever and see what happens. You can see a command block saying that pressure plate has been activated, so let's go over there and see what happened. And you can see that a falling nether portal block has been spawned, and you could actually then push this falling nether portal through an end portal to get nether portals in the end. So that's one potential use case of this. Just quickly, briefly, how it works. The nether portal is being lit on the main thread, while the async observer line is updating some sand inside of it in the beacon thread. So the nether portal can place the sand as it is trying to fall, and then turn into a falling nether portal block, which then gets pushed out here onto this fence. Just a very brief explanation. On my computer, to get this to work consistently for the video, I had to add this bit of code here, just basically telling the thread to sleep so that I don't need 1,000 retakes. For some reason, it's really rare on my computer, but for everyone else, it's been basically like 1 in 10 or 1 in 20 sort of thing. So we don't know why it's so bad on my computer, but there you go. Just to be transparent about that, this is slightly modded, but it shouldn't need to be. So thanks for watching. Make sure to watch the other people's videos again, and I want to mention that while recording this video, there have been other uses of falling block confirmed, such as getting water in the Nether, although not in the way that you might think. So yeah, anyway, see you in the next one.